Thank you, Enric, and thank you, all of you. It's a pleasure to be here with you today, and I'm going to tell you a little bit about the James Webb Space Telescope. I think looking at the sky, now we live in cities, so we don't see it so much, but in the olden days, that's what we had to tell us the change of the seasons, to travel, looking at the North Star, etc. And as we learn more with science, when the telescope was discovered, we were able to advance our knowledge and we got to understand, unfortunately, the Earth is not the center of our solar system, and also that we don't live on a single galaxy. There are millions of them. So after developing this telescope, we were building some on the ground, and we have a lot of them to be able to look at the space. You can see there, the next thing we realize, of course, is that the Earth has an atmosphere that's going to affect the observations that we do on the ground. The atmosphere is going to move, it's going to do a little bit of blurring of any image you want to take. But also, as you can see here, this atmosphere protects us from some radiation, which is good for us because we need to live here, but it's not good to look at some of the wavelengths where the space gives us information. You can see there that from the ground we can definitely look on the optical with some limitations, and we can look on the radio, which was used, for example, during the war, right? We have the big radio telescopes where we can collect then the radio signals that come from space. But we are not able to look any of the high energy emissions, and we cannot look in one particular wavelength we are going to talk today, which is the infrared, which is what James Webb is designed to do. And if you think about the objects in the sky, they are going to tell us about what they're doing and their lives in different wavelengths. So if we want to get a complete history of what's out there and how it evolves, we do need to take pictures in all of them. So in the middle of this century, not so long ago, we had the first satellite, the Sputnik, 1951, and that opened a new era. Again, we are learning, and we are now able to send satellites into space for many things. Of course, observing the Earth, our phones, GPS, lots of things we are familiar with that are part of our everyday life, but that before were not possible, but also be able to send these telescopes into space to be outside the atmosphere and then to look at all those other wavelengths. And as it was mentioned before, I think everybody is very familiar with Hubble. Hubble orbits the Earth about 600 kilometers around the Earth, and it was designed to look mainly as our eyes in the visible. And I think a lot of you know when it was first launched, it had a problem. Its mirror was slightly misaligned, so the images that it sent to the ground were fuzzy, so it needed some glasses to correct its problem. And to do this, because it orbits the Earth, there were missions with astronauts that could go and fix Hubble, and then also there were another 4 extra missions where they could go and install better instruments for observing. Hubble was designed, as any big telescope is, you have to have scientific goals in mind to get the agreement for the telescope to be built and get your budget. And in the case of Hubble, there are many great things that it did. But when you look at the universe in a different way, you always find things that you didn't know about, and it increases our knowledge. This is one of my favorite images from Hubble. This is a part of the sky, is about like a postage stamp. And if you look at it from the Earth, it's dark. There is nothing there. So, of course, we knew there was nothing there because we had looked at it from the ground, and it was part of our knowledge. But once Hubble was on orbit, there was a proposal to observe this part of the sky for a few days just to make sure there is nothing there. And this is the image that came down to the ground. And there is hundreds of objects there. They are all galaxies. So again, it taught us more than we knew, and it emphasized again how big this universe where we live is. So if we move then to the next, as was said, the brother of Hubble. This is the next telescope. It's called its successor. In reality, they are both going to be observing in parallel for a few years. Hubble, and there is no further funding to do any more repairs or to that telescope. Again, it's always a case of how much money you have and what can you fund. So Hubble will still last for a few more years, but then it will end. James Webb is launching at the end of this year, so I hope you'll all cheer and watch that when it happens. But for a few years, both will be observing together, which is going to be really good because James Webb is looking at the universe with different eyes on this infrared. And this is a top-level picture of what are the main components on James Webb. And the first thing we are going to notice on James Webb is that it has a part that's going to be very cold, which you can see is on the top. In there you can see the mirror. The light goes, here I have, okay. Yes, okay. So you have this big mirror. We are going to talk about that mirror a little bit more. The light from objects in the sky will come to this mirror. It will bounce back and go into this secondary mirror, and then it will bounce from that mirror and go through here. There is a tertiary mirror there, and all the instruments are packed in the back of the mirror. All this part of James Webb needs to be very cold. It needs to be very cold because we are going to observe in the infrared. The infrared, you can understand it as heat, and everything emits heat. So you're looking for images from things that are very faint, so you need to cool down everything else. Otherwise, you won't be able to detect them. So this part is going to be at 40 Kelvin, very close to absolute zero, about minus 233 centigrades. But on this side is where we have the electronics. The electronics don't like to be that cold, so we have to keep them warm. And then we also need to be able to cool down this part to those temperatures. And to do this, we use this Sunshield, this a beach umbrella. So this is, if you were on the beach, this is the part that will always be on the shade. And on this side, it will always be facing the sun, the moon, etc. So this part here is going to be very hot as 88 centigrades. So one of the challenges for James Webb is not only that you're building something that's going to be operating so cold, but also that you have a hot and cold zone, and you don't want the heat from the hot to go to the other areas. So there is a lot of complexity for many of the team members involved to develop and have it ready. This is a model of the James Webb in real size. So you are going to notice the next challenge, which is that it's very big. It's the biggest telescope that we will have launched into space. And we are going to talk a little bit about why we did that and how are we able to launch it. Because you can clearly see you cannot fit this thing in a rocket. I mean, everybody can notice it. And this is a very small fraction of the team. And this is the center where I am based, Goddard Space Flight Center, just outside Washington, D.C. So let's compare Hubble and James Webb, which people are very familiar. So if Hubble was here with us, it would be as big as a school bus. If James Webb is here fully open, its Sunshield is as large as a tennis court, and in height it's about 4 floors high. So it's a much bigger size to launch into space. Having said that, James Webb is lighter than Hubble. When you launch something into space, there are certain requirements you have to meet. One of them is how much it weighs. The heavier, you need bigger rockets to be able to launch them. So you learn to use materials and processes that make what you are launching lighter. And of course, we have learned a lot. We can launch something bigger that weighs less than what we launched 20 years ago, which was the Hubble. The other important difference is the size of the mirror. So a bigger mirror allows you to collect more light. It's a bigger bucket, you're going to get more light, so you can see fainter things. And that's a great idea. You can see James Webb is much bigger, but you immediately run into a problem. I want a bigger mirror, but it has to fit inside this rocket. It cannot fit, so great idea. Let's make the mirror out of 18 smaller mirrors that I can fold. I'll fit it in, and then I'll open them and align them when they are in space. And this is a great idea, but then, of course, you have to make it reality, which, again, was another one of the challenges of the James Webb. And then the other thing is where it's going to be. Hubble, as we said, is around the Earth. We were able to service it. James Webb is going to be in one point that Pedro mentioned, L2, the Lagrange point number 2, which is about 1.5 million kilometers from the Earth, about 4 times the distance of the Moon. These are special points when you have 3 bodies, as a lot of you probably know, when you have 3 bodies in a space and you do the math to calculate the effect of the gravity for all of them, you will find 5 points where those gravities annul each other. So if you put something there, it's going to be pretty stable. So L2 is one of the positions. If we take the telescope there, it will mostly stay there. We have to do little corrections to that orbit. It's not 100% stable, but it's a good place. And also is away. The sun is on this side, and the Earth and the Moon. So we want to be cold. We want to be as far as possible from the sun, and then we can then put our Sunshield pointing in this direction. So the Sunshield is always going to be pointing to the sun and the Moon, and we are going to be rotating like the Earth. So the mirrors and the instruments are always going to be cold, which is what we need. And then the other main difference, which we already talked, is where are we going to look into the sky, and we are going to go into the infrared, and we are going to talk a little bit more about what that means. Every time you design a big telescope, you're going to commit a lot of resources, a lot of money, and a lot of time. So it has to be an agreement. The scientists have to do a strong case why this telescope makes sense. So James Webb has 4 main themes, which were the drivers for its development. One of them is we are going to look back in time to the first stars and galaxies that were formed in the universe. Sometimes when you talk about looking back in time, what's going to happen is those first objects that were formed after the Big Bang, when they turn on, those stars emitted light. That light has been traveling through the galaxy, the universe is expanding. So what that does to the light is its wavelength is going to stretch. So if you saw on the previous picture, you can see here when we are in the visible, this is the kind of wavelength that we have. Once we go to the infrared, it's not as noticeable here, but you see how the wavelength stretches. So if you stretch the wavelength, what you are doing is moving into the infrared. So if I want to detect that light from those objects from so long ago, 13.5 billion years, you need to take a picture over there. If I take a picture on the visible, I'm only going to collect the light of objects that are closer to me. They haven't traveled that far. So James Webb is going to look at those first objects that were formed. There are theories of how the formation of stars and galaxies occurred and how it evolved to the one where we live. This is an example of a galaxy where we live. We live in one of the arms of the galaxy. There are different types around us, different types of galaxies. We know about them and we have classified them. But when we start looking back in time, these are some pictures from Hubble. Hubble could look back in time a little bit, but not far enough. And you can already see these galaxies don't look like the one where we are now. So obviously there is a process of galaxy formation and evolution that we want to understand to see how we got where we are. James Webb is also going to look at the formation of stars and planets. Again, we know those first stars were much bigger. We know they only had helium and hydrogen because those were the only elements at that time in the universe. We know those stars exploded and formed all the other elements, which is how we are made. So again, James Webb is going to look for information on how that happened. And then James Webb is going to look for the other big question that I think we all have. Are we alone in the universe? So if we had this talk 20 years ago or so, and you ask, well, are there other planets in other stars? We could say, I think so, I don't think so. We wouldn't know. Since then, we have had a few telescopes, Kepler tests, that were designed to look for planets around other stars, and now we know there are hundreds of them. And this is a popular technique to detect a planet. If I look at a star and I have the light of the star and that star has a planet, when the planet goes in front, the light is going to go down a little bit. So I will say, hey, there is a planet there. Of course, it's easier said. If you think about it, the light is going to dim a very tiny amount. So you need to develop a strong math to say, yes, I see that little change. Sorry, I see that little change, and there is a planet there. So those techniques have been developed, and now we have a range of planets. James Webb is going to look for planets, but mainly is going to look at some of the planets we already know and look at their atmosphere. And what we're looking for is, does that atmosphere has water, methane, carbon, things that we know are needed for the life as we know it, and start ruling out how many of the planets that we already know have those conditions. Infrared, this is why we want to look on the infrared. These are the picture of the same part of the sky. This is a star, a part of the sky where we know planets and stars are being formed. They are always formed where you have dust and gas, which means we can detect formation is occurring, but we cannot see it indivisible with our eyes. It's dark. If you look on the infrared, you can detect the heat signature of those objects, and this is what James Webb is designed to do. It doesn't matter what's there. I like to mention it's like in the movies, right? It's night, you don't see anything. The bad guys or the good guys put their glasses, and suddenly, oh, you can see the heat. Somebody's walking over there, even if it's behind the house, etc. It's a similar idea for James Webb, to look at the universe on a different way. So James Webb is an international collaboration. So it has a contribution from NASA, obviously, the United States, but it has 2 instruments coming from the Canadian Space Agency, which is where I started working. And then it has 2 instruments, MIRI and NIRSPEC, which come from the European Space Agency. So it's an international collaboration. These are all the flight models, the instruments arriving, and this was an incredible moment where they were all put together as precisely as they need to be put for them to be together. And I remember showing this picture to my family in Spain, and they were like, okay, you just put them there together. Hey, there they are. Because it looks messy, but that is not true. They are all precisely where they need to be. If you think this instrument is going to be operating so cold, but we cannot work in those temperatures. So we have to build them at ambient, knowing, as you know, if you put something in the freezer, is going to change how it looks. So the same happens here, right? I build it at ambient, pointing here, knowing when I make it that cold, it's going to point here. I need to know how to operate it when it's that cold. So there is a lot of modeling and a lot of detailed work for many team members to know where everything needs to be. We talked, the instruments, we could talk a lot about them, but we don't have time today. So let's look at the other component, which is the mirrors. This is the clean room at Goddard Space Flight Center. It's one of the largest clean room in the world. And here is a special structure. These are the 18 mirrors. They arrived, each of them built and individually ready. They arrived to Goddard, and another team expert on this put them all together. There they are. They have a cover on top because a clean room is a place where you keep everything really clean before you launch it into space. So a mirror in this direction is kind of the worst thing you can do, because anything is going to land on your mirror. So whilst they were being built, you put these particular covers to protect them. And I love this picture, again, very trained. You can see the 2 team members of this part of the project removing carefully the covers to show what is the most famous, one of the most famous features of James Webb, which are the mirrors. The mirrors are coated, they are made of a special material, beryllium. Like all the components on James Webb, they are materials where you try to minimize how much they change when you go cold. And also we are going to take them cold and warm them and cold and warm them as we test them. So we want them stable. I don't want to go cold and I say, yeah, everything looks great. I warm it up. The next time I go cold, hey, it's pointing over there. No, I mean, you cannot have that. You have to be very repeatable and know precisely what happens. So the mirrors, this material, beryllium, is very good for that. It's also lightweight. But then they have a coating on gold. And if you think about it, the mirrors you have at home are coated in silver, aluminum, because that's what you need to reflect the light that our eyes can see, which is the visible light. James Webb, if we looked on the infrared, our mirrors at home will all be gold. But that's what James Webb needs. So You build a telescope, it's going to be really far, and you have to test it really well because we won't be able to go and fix it. So testing it involves when you launch something into space, which a lot of you, again, know about this. One of the worst parts of the journey is the launch. You're going to go on a rocket that's going to shake what you launch, and it's also going to be really noisy. So it's always very important that you do your vibration and acoustic testing to make sure your payload is going to survive. And to do that, we need to go to special chambers. It means we have to take the telescope from this clean environment, this clean room where we were keeping it clean. And here it is. It's already kind of folded as it's going to be on the rocket, so it can fit. And you can see we put a particular cover over it to protect it whilst it's outside that clean room. So vibration and acoustic, very important when you launch something into space. But then the other important thing is, as we said, duplicate the conditions that your instruments are going to see. So you need to put them in vacuum. And in this case, you need to put them at 40 degrees Kelvin, minus 233. So to do that, we have these big freezers. We have the one at Goddard where we tested the instruments. But once we put the mirrors together, the chamber at Goddard is not big enough, so we had to go to Houston. The chamber at Houston is well known because that's where the testing to go to the moon for the Apollo program happened, so we had to refurbish the chamber. This gives you an idea. This is the front door, and there is another 8 floors. This is how the chamber looks like. This door here covers a portion. You can see here the telescope. So the chamber at Houston allowed us to do something very important, which was to open the full mirrors and do some of the testing we need to do on flight. The instruments are still here on the back. And the rest is, I'm testing it, but I need the stars, right? Otherwise, I won't know what to test. So every time you test, you have a lot of effort on what ground support equipment, things that you need to be able to test what you need to test. So that, again, another big clever part of the team that looks after that. And here is, you can see that same door. Here is the James Webb about to go in. I can tell you, I know they knew they had done all the measurements, but when you were looking at this and the door, you were like, oh, are we going to fit? But it did. I mean, of course, they knew it was going to fit. It went well. We tested for 3 months, 24/7, at the cryo temperatures that we needed to do to confirm everything was working. So the question that comes up is, how do you move such a telescope around? We had to go, here is Goddard, and that's where the instruments and the mirrors arrive. We did the first tests there. Then we have to go to Houston, which is down here. And then after that, there is a part missing still on this telescope, that Sunshield that we looked at before, and the spacecraft bus are not there yet. They were being built in parallel in Los Angeles. So we are going to go to Los Angeles. So we have a special container where we fold it the same way that's going to go on the rocket. And you can see here we use a military plane, an A5 that we can open, and then this track goes overnight, right? I mean, it goes very slow, 5 kilometers per hour. You can kind of walk with it. You have to remove the cable. So again, another team, which Pedro mentioned as well. I think going into space is where you mix lots of skills from different fields, which I always tell people, we need mechanics, electronics, software, transport, etc., to make these big telescopes. So whilst we were having all the fun with the instruments and the mirrors, the team at Northrop Grumman, which is one of the contractors in the United States, were having a lot of fun with the Sunshield. So the Sunshield is a key component of the telescope. It's 5 layers, as big as a tennis court. It's made of special material, again, Kapton. That's very common when you go into space to develop these type of materials that then we end up using on the Earth as well. And you see here the layers. The main purpose is to cool down, to let the telescope cool down, remove any heat from the warm side. So we like to say if you're behind the Sunshield, your SPF factor is 1 million. You're not going to get tan ever, ever, ever. You can be on the beach. And here is us arriving to Northrop Grumman. So here is the mirrors really folded. The instruments are on the back. This is how it will be on a space. And this was in 2018. And here is the Sunshield. You cannot quite see it yet. You'll see it a bit more. Here is folded again, as it will be to be able to go inside the rocket. And it has a protective layer, which is indeed this color, this light pink. And here you can see, to do their testing, they didn't have as our component. So they have a model here. They can do their vibration and acoustics, but they need to simulate everything else that's going to be with them. Otherwise, those tests are not important. And here is a year later, we managed to put it all together, and this is open up, not fully. This is how it will be in a space. You can see the side mirrors are still back on this particular picture, and that secondary mirror is folded up to fit in the rocket. So this is a picture of an intermediate test period. So we are almost done there. We finished all the testing there, and we are almost ready to travel to where the launch site is going to be. So the launch site is going to be in the French Guiana. And it's a contribution. We are launching on an Ariane 5 rocket, which is, I indicated it was an international collaboration. That's another contribution from the European Space Agency. So Ariane launches from the French Guiana. We are going to go by boat, in this case, through the Panama Canal, which, by the way, charges you per weight, which is something I didn't know, and this is very helpful. So they're very happy that we're going through there. We are about 6,000 kilos, so a good size. And again, you see, this is the same container as before. So the only difference now is that instead of this going inside a plane, it's going to go inside a boat. And travel, it will take about 2 weeks to get there. And here we are. This is the Ariane rocket. It's always amazing to me how much of the rocket is the fuel to get us out of space. And this is the payload. Here we are on the top. You can see all the mirrors folded. The Sunshield is folded here. And then once we launch at the end of this year, we'll start traveling to L2. We are going to take about a month to get there, but then we have another 5 months to do all the other extra operations that we need for the telescope to be ready for normal observations. I'm going to show you a little video to see what's going to happen. Within a few minutes of launch, we start our deployments. So as the telescope, travels, we have to start opening it. And we have that, we have, again, a big team where we know exactly what we are doing from the launch for those 6 months. We have it planned minute by minute, so we know what needs to happen. Let me see if this plays. Okay, here. Okay, so this is a few minutes after launch, because you see we don't have the rocket anymore. You saw there how we are getting the antenna that we need to communicate from the ground, and I don't know if you saw it quickly, our solar panel. We have a battery when we launch, but we need to start getting power from the sun as soon as possible. And then you see here, you saw how the Sunshield was folded. The 2 pallets are coming down. This starts about day 3 after launch. And in about 3 days, all of this will happen, and they will stretch out. They need to be tensioned, and then we have 5 layers to be able to achieve the heat loss that we need, and they need to be tensioned, and you can see them here. And that happens as we are traveling on our direction. And then this is key the solar panel is key. We cannot operate if our battery runs out. We need the antenna as well as key. We need to be able to communicate. We need the Sunshield to allow us to cool down, and then we need the mirrors to come down. Now, the critical mirror is the secondary, because we need the light to be able to bounce to the instruments. If the side panels didn't happen, we have a backup plan to work that way. Once we are in this on this display like this, which will be about 30 days after we launch, then we can start calibrating all the instruments. So James Webb is important from a science point of view, but it's important from an engineering point of view. It's the first time we are launching a deployable telescope into space, and once we demonstrate this capability, other larger telescopes will be able to occur. There is a very important period after all of this is open, which is to align the mirrors. I mean, it's a great idea to have 18 mirrors. When I take my first picture of a star and I look at the image on the ground, I'll have 18 stars, because each mirror is taking a nice picture. So we spent about 2 months moving those stars so they're a single star and making sure it has the right profile. And then after that, we take another 2 or 3 months to calibrate each of the 4 instruments that the James Webb has, and then it's open for science. So I hope you all watch it when we launch, and that you follow us, and thank you for having me.